Hello! Today I bring to you Analysis 1B, yet another integration technique. So this is our second lesson in the integration techniques unit. Oh, it's very off-center. Our second lesson in the integration techniques unit. This is the lesson that you will be watching prior to the October 1st or second class, depending on which period you have. And in our lesson today, students will be able to, this is not going to give you much info until we come back at the end, but that's okay. Students will be able to OIGOIG and also to EFUSOT. Today, you will learn to OIGOIG and EFUSOT, and this is our plan. So this is a follow-up. The next lesson after integration by parts. So here we go. Integration technique. Big integration technique number 3, I suppose, right? U sub, then integration by parts. And now we will be OIGOIGing and EFUSOTing, I suppose. All right. Task 1. Task 1. For your consideration, please consider the following integrals. We could consider the integral of sine x cosine x, as well as the integral of sine squared x cosine x, dx, that's a vital part to the integral, as well as, say, the integral of sine squared x cosine squared x, as well as the integral sine cubed x cosine x, as well as the integral sine cubed x cosine squared x, as well as the integral sine cubed x cosine cubed x. Let's think about if that covers everything I wanted. So I have 1 and 1, I have 2 and 1, I have 2 and 2, 3 and 1, 3 and 2, 3 and 3. Let's add a few more. Let's talk about sine to the 4th x cosine x. And let's talk about sine to the 4th x cosine squared x. And sine to the 4th x cosine cubed x. And there's where I'll stop. There's where I'll stop. So why am I putting this many integrals on the page, right? You should stop for a sec. You should pause. I'll probably add a question here, to be honest. And you should be thinking, if I had to do these integrals, if I had to start somewhere, where's the, I don't want to say easy, because none of these are necessarily easy, right? But where is the least bad place to start, right? Where is the least annoying place to start? And I really do encourage you to pause for a second, think about that. And I don't mean just one, like order these in a sense, right? From the most straightforward, from the least bad to work with, through the ones that you really don't want to have to do, right? That's the goal here. I think it's fair to guess that most of you would say, most of you would agree, that maybe starting with the integral of sine x cosine x would be a decent start, right? That seems plausible to me. Sine x cosine x seems like a decent start. So let's talk about that one. If we're going to be doing the integral of sine x cosine x dx, there are many ways we could do this. For one, we could use an angle identity formula, trig formula, I mean, double angle, and turn this into 1/2 sine of 2x and integrate that way. We certainly could. But we could also do a direct substitution here, right? If we use that u equals sine of x, then du would be cosine x dx, and I would get the integral of u du, which is, of course, u squared over 2 plus c, and therefore sine squared x over 2 plus c. And if you use a different method, you might get this answer in a different form, but you could show with some trig that they are equivalent. So there's option 1. Of course, some of you might have looked at this and thought the other way, right? What if instead we substitute for the cosine? Du would be negative sine of x dx. Doable, not a big deal. So we get an integral of, I don't have the negative, so I need a negative factor to cancel that back out. But then the sine x dx gets used, and I have a u du, right? The cosine became u this time, and the sine x dx became negative du. for a total here of negative u squared over 2 plus c, which gives us negative cosine squared over 2 plus c. And if you stop and think about it, like, yeah, these do end up being related. That makes some sense because I could replace the sine squared with 1 minus cosine squared, or the cosine squared with 1 minus sine squared. And I would end up with a constant plus the other plus c. And the constant would get absorbed into the c, right? This c could get replaced with 1/2 plus itself, and that doesn't make a difference. So although they look different, these are the same value, right? They end up being the same function. So that one I would agree, right? That seems like a good starting point. Seems reasonable. Okay, what next? Right, what next? And again, having taught this a bunch of times, I think it'd be fair to suggest, fair to guess, that most of you are thinking sine squared times cosine as a good second step. So let's try that one. Let's see what happens, right? Sine squared times cosine, a reasonable second step here. So number 2, we're going to be doing sine squared times cosine. So the integral of sine squared x cosine x dx. So just like last time, we can think of doing it both ways. We can think of doing it 2 different ways. One way would be that u is sine of x, and therefore du is cosine x dx. No problem. In which case, my cosine x dx becomes du. I have u squared, but that's fine. I can work with that. So I get u cubed over 3 plus c, which would be sine cubed x over 3 plus c, right? No big deal. Oh, I'm off the screen. I'm sorry. Sine cubed x over 3 plus c. No problem. So let's try it the other way while we're at it, right? This should work in multiple ways. Seems plausible, seems reasonable. So if u is cosine, du is again negative sine of x dx. So if we look at our integral now, let's go to the original integral here. I had a sine squared x cosine x dx, which I can think of as I've got a sine x that I'd like to keep here with my dx. I'm going to use it in my sub. And then I have a cosine x and another sine x sitting around. So the cosine x here becomes a u, that's fine. The sine x dx becomes negative du, that's fine. I'm not subtracting, right? It's a factor of negative du, so we'll get a negative out front. But then we still have this sine sitting here. I'd have to convert that to u's somehow. So if we go back to our u expression, like, well, u squared is cosine squared, but now I've got to be careful with SIGN signs. So if u squared is cosine squared, then u squared is 1 minus sine squared, and I could solve for sine, and I could plug in a square root, and I could... This does not seem like a good plan to me. We could do it, in theory, but it seems way more complicated than subbing u equals sine this time, right? Which does make some sense. In the previous problem, we had a symmetry, so to speak. We had sine to the 1, cosine to the 1, so it really shouldn't matter which one we work with. But now we have sine squared, but only a single cosine. So it does matter which one we work with, and that feels reasonable, right? That doesn't seem implausible, that there would be a difference between subbing for one versus the other. So let's not do the u sub. I'm sorry, let's not do the u sub of cosine, right? Let's do the u sub of sine in this case. That feels better to me, right? That worked out pretty well. And this was indeed our second problem that we tried. No big deal. So we're back to the list. And the question is, what's a reasonable third thing to try? And for likely the first time, I'm hoping that we have some disagreement among students here, that this isn't as obvious to you anymore. On the one hand, just going in order, right? Sine squared, cosine squared doesn't feel like it should be much worse than anything we've done. But some other people might be considering, well, instead of incrementing both powers, let's increment only one of the powers, right? Let's let the sine power go up but keep just a cosine maybe, and maybe that'd be easier. So here's where it starts getting less obvious. So I'm going to keep going in order for the moment, but I want to kind of compare these two, right? So I'm going to treat these together as the third step that we're doing, because I want to compare what happens when we try to do them. Not because they are the same difficulty, but because I want to compare what happens. So I'm going to try to fit all 3 on one page here, which is going to get a little tricky. Oh, I'm sorry, 3 different approaches, I should say, on one page here, which is going to get a little tricky. Maybe even 4, so bear with me. We have sine squared x, cosine squared x dx, and I'd like to try 2 different subs for that. And we're also going to be thinking about, at the same time, sine cubed of x, cosine x dx, and I'd also like to try 2 different subs for that. So let me make this middle one thicker. So I really want to compare all 4 of these cases, right? We're going to try a u sub of u equals sine. We're going to try a u sub of u equals cosine. We're going to try a u sub of u equals sine, and we're going to try a u sub of u equals cosine. And we're going to kind of see what happens as we try these different setups, right? We try these different permutations. All right? If u is sine, du is cosine of x dx. So I'm going to take one of my 2 cosines and use it in my du. The sine squared just becomes u squared, so I end up with a u squared, but I still have a cosine left over when I get my du, right? I've used one of the cosines in my du, but the other is still sitting there and I'd have to convert it somehow. This is the same problem we had a minute ago. If u is sine, there isn't a particularly good substitution, a back sub, as I call it at least, right? Going back to my formula and substituting again to get rid of that cosine part. So maybe this is doable, but not directly in this way, right? The substitution of u equals sine is not a straightforward substitution that we can just finish easily. And I hope that you've already noticed that analogously, the same issue is going to come up trying to sub the cosine. First of all, I get a negative, but that's not a big deal. I'm going to use one of my sines with the dx, but that leaves me with the other still. And I still have a u squared du. So now this sine, in turn, doesn't let me finish easily, at least, right? This might still be doable this way, but not in a direct way, not in a nice way. Let's try the other side. Or better, let's be very clear here, right? What would I have to do? I'd have to say that u squared is sine squared, which is 1 minus cosine squared. I know I'm at the very bottom of the page here, but bear with me. Which means if I'm trying to solve for a cosine, which I could try, but if I try to solve for cosine, I'd get a square root involved, right? I'd get that a single cosine is a square root of 1 minus u squared, and I'd have to substitute in a square root, and that would get messy. That's the key here. That's the idea. Let's try the other side. If I sub for sine, I get that du is cosine of x dx. So when I sub in, my sines each become a u, so I get a u cubed, and I use my cosine, right? Cosine x dx, du. No problem. U to the 4 over 4 plus c, giving me sine to the 4x divided by 4 plus c. That worked out beautifully. No big deal. Let's try the other side here. If I sub u equals cosine, then du would be negative sine x dx. So I have a negative like before. I'm going to use one of my sines, which means I keep a pair of them. My cosine x becomes a u, and my sine, the one that I'm using of the 3, helps me get my du. So once again, we're left with this term that we have to back sub for, that we have to go back to our substitution relationship and figure out how to get rid of it. But why is this different, right? Why is this nicer than when it happened over here on the left side of the page? Why is this better? Well, think about the sub that happened at the bottom here, right? In this case, if I try to figure out this sub, I would say that I know that u squared is cosine squared. So u squared is 1 minus sine squared. So sine squared is 1 minus u squared, right? And I can do that sub. I don't have terrible square roots floating around. It's still not as nice as the version of substituting for sine, but it's also not awful, right? I get a 1 minus u squared and another copy of u and a du. And that's just a polynomial. This is multiplied out, right? You get u minus u cubed. That's something we can do without too much trouble. So what we get, sine squared cosine squared was actually kind of messy no matter what we did, right? We'd end up with square roots times u's on the outside. Sine cubed cosine, not so bad. If you sub for sine, at least. And if you sub for cosine, it's also not terrible. It's not as nice as subbing u equals sine, but it's not awful. It worked out okay. We had to back sub, but we didn't get square roots. We didn't get anything messy. It works out all right. So what do we learn out of this? Notice I'm not finishing that off, right? You can finish that if you need to. What do we learn out of this? Turns out, let me use the colors so I don't like mess things up, right? This one was great. Worked both ways, in fact. This was good, but it was much better when I substituted for sine than cosine. So I'll make a note of that. And now the sine cubed cosine works pretty well. I can actually do it either way, in fact. One of them I get a polynomial. It's a little messier, but at least I avoid square roots. However, sine squared cosine squared, that messy no matter what I did, right? That was messy either way. That was not fun to deal with. Let's back up and make sure we can deal with it, though. Like, let's go back to that problem and make sure it's something we can do, which it is. If we're trying to integrate sine squared x cosine squared x, here's your key. We can talk about this as being sine x cosine x quantity squared, which in turn gives us 1/2 sine of 2x quantity squared. So we get a 1/4 and we get a sine squared of 2x. And now the question is, how do we integrate sine squared? Well, we've been expecting you to do that for a while at this point, right? We've been doing those problems. We use our our power reducing formula, which for me, I have to start in the same place every time. I have to start with the cosine, I'm going to be careful here, cosine of 4x would be cosine squared of 2x minus sine squared of 2x. And then I'm going to replace that cosine with 1 minus sine squared. So I get the cosine of 4x is 1 minus 2 sine squared of 2x. And there's my sine squared of 2x I was looking for. I can solve for it. Flip sides, divide by 2. So my integral ends up being a 1/4 still, that's out front. And then I get 1 minus cosine of 4x all divided by 2, which we can integrate. It's not too bad. We have a 1/2, no problem, and we have a negative 1/2 times cosine to the 4. I'm so sorry, not cosine to the 4, but cosine of 4x, right? And you can think of that as a formal u substitution itself, u equals 4x, or you can just kind of do it in your head, right? But either way, this works out okay. So what happened here, we couldn't just do a simple substitution, right? I couldn't just sub u equals sine or u equals cosine. I had to come up with a different way. Unlike the other problems we've done, this one requires power reducing instead of doing a straightforward trig sub. I'm sorry, a straightforward u sub, I should say. Still doable, but I would argue more annoying, right? I would argue the sine cubed cosine was actually nicer to work with than the sine squared cosine squared. All right, we've got 1, 2, 3, 4, 5 more. What next? What next? And here's where you want to start thinking about the pattern. Think about what's been happening every time. So let's go back to the slides and look. When I had sine to the 1, cosine to the 1, subbing a sine used the cosine that was left over. Made it easy. Or subbing cosine, it used the sine that was sitting there. Made it easy. When we tried sine squared cosine, when I sub for the sine, we used the cosine that was sitting there. Not a problem. But when I tried it the other way, I used one of the sines, but that left the other. right? That left the other, which would end up being that whole square root mess, right? That'd be annoying. For sine squared and cosine also squared, when we used the sine, when we sub for sine, we used one cosine, but it left the other, so we add a square root. When we tried subbing for cosine, it used one of the sines, but it left the other. We add a square root. With sine cubed cosine, when I sub for sine, it used the cosine. Wonderful, no problem, made it easy. When we sub for cosine, it used one of the sines. That left me two of them, which means I still had to get rid of those, but since there were two of them, I could just use a Pythagorean identity directly, right? I didn't need to work with a square root. My sine squareds replace a cosine squared, and it works out nicely. Not so bad, not so bad. And we realize for sine squared, cosine squared, we have other techniques we'd have to use, right? Angle identities, trig identities. I keep saying angle identities. So what now? I hope that you would agree. I'd hope that you have noticed that perhaps this sine to the 4 with a single cosine would work out nicely. And indeed it does. Let's do it and see. So I'm going to, as the fourth thing we consider, I'm going to consider this case of sine to the 4 times cosine. So for our fourth case, we have an integral of sine to the 4x cosine x dx. And I hope that you can already predict what a good substitution to use here should be, right? If we sub u equals sine, then du would be cosine of x dx. How wonderfully convenient. We have exactly a cosine x dx. So we end up with u to the 4 du, right? I use the cosine x dx. Everything's great. I get u to the 5 over 5 plus c, which is sine to the 5 over 5 plus c. No big deal. We should try, for completeness sake, we should compare what happens if I try to sub for the cosine. Du, as every time thus far, is negative sine of x dx. So when I sub, of these 4 sines, I'm going to steal one of them. So I'm going to keep 3 of them here, sine cubed x and my cosine of x, and then I'm going to keep track of the remaining sine. I'm going to group it with the dx so that I get a du and I get a u, and the question is, what about sine cubed? Well, 2 of those, right, sine squared of x can become 1 minus u squared, same as before. Square u squared equals cosine squared, and then replace the cosine with 1 minus sine squared. So I could get a single sine left over and a copy of 1 minus u squared and a copy of u and a du, but now we're left with this single copy of sine again. So we'd get another square root, right? We'd be stuck with some kind of square root of u. It would be annoying. Fun fact, it would actually be impossible based on techniques you currently know, other than just going back. So once again, this didn't work out nicely. On the other hand, subbing for sine was great, right? I wanted a cosine, I had a cosine. No big deal. No big deal. Okay. So this worked out pretty well. I needed to sub the cosine specifically, right? I'm sorry, the sine. I needed to sub for the sine, and then it worked out nicely. All right. That was okay. 4 left. Now what? 1, 2, 3, 4. 4 left. Now what? I'm also running out of colors. I have brown. I use brown. All right. There's no correct answer here, just so you know. There's no, like, of these 4, one of them is definitely the best to go next. I would have argued among the 5, this one, the one we did 4th, was definitely the best to go. But among the remaining 4, there's no correct answer. There is, however, a wrong answer. One of these 4 is notably more difficult than the other 3. And here's where I'm going to insert a question to make you answer that, right? One of these is notably more difficult than the other 3. And it's based on what we've been recognizing. So let's think it through. If I sub u equals sine, I want a cosine to use to get my du, right? If I sub for sine here, I use the cosine. If I sub for sine here, I use the cosine. If I sub for sine here, I use one of the cosines, and I'm left with a cosine. That was annoying. On the other hand, let's think about subbing for cosine. If I sub for cosine here, I use the sine to get my du. That was okay. If I sub for cosine here, I use one of the sines, but I'm left with another. That was annoying. However, here, if I sub for cosine, I'm sorry, wrong one. Here, if I sub for cosine, I use one of the sines. I'm left with two of them. And being left with sine squared wasn't so bad, right? Being left with a single copy of sine was terrible. I'd get square roots. It was annoying. But being left with sine squared worked out okay. That wasn't so bad. Up here, if I sub for the cosine, I used one of the four. I'm left with 3. Of those 3, a pair of them, sine squared, isn't so bad, but I'm left with a remaining sine by itself. It would be a square root involved if I tried to back sub, right? That's annoying. So what are we noticing? What are we noticing? For every problem of the 4, not this one, but for the first, the second, the better of the third, and the fourth, subbing sine was great, right? I had exactly one cosine. That was wonderful. I subbed it. It went away. It was used for my du. When I had 2 of them, though, it was a pain. And let's think the other way. When I sub for cosine, having 1 sine was okay. Having 3 sines was pretty much okay. But having 2 sines or 4 sines was bad, right? Because one of them gets used for du, and I'm left with a setup where I can't just use cosine squared and sine squared as 1, right? I'd have to get a square root involved. So with that idea in mind, we're down to 4. We're down to 4. And here's where the question is for you, right? Which of these is the odd one out? Which one is the one that's hardest of the 4? Sine to the 4 cosine squared is going to be the worst. Let's think about why. If I try to sub u equals cosine, then of the 4 sines that I have, one of them gets used. I'm left with 3. I can't easily use a sine squared cosine squared relationship. If I try to sub for sine, I'd get u equals sine, du is negative cosine x dx, and I'd use one of the cosines, but I'd be left with the other still, and my back sub would be a square root. On the other hand, let's try these others. Let's take a look. And let's kind of figure out what the sub is we should be doing, right? Instead of writing it all out, let's just figure it out. For, say, sine cubed x cosine squared x dx. Let's think it through. If I sub u equals sine, then I'll be left with a cosine x. Oh, I'm off screen, right? I'd be left with a single cosine x. I use one of them, I'm left with the other. One gets used for du, the other gets left. So this would require a square root, and I don't want to do it. On the other hand, if u equals cosine of x, then du would be negative sine of x dx. So I get a sine squared, and I use one of the sines. I need my negative out front. So I get a u term, I get a du term, and I get, this isn't so bad, right? If u equals cosine, then u squared is cosine squared. So u squared is 1 minus sine squared. So sine squared is 1 minus u squared, right? I can work with that. I'd have a negative of the integral 1 minus u squared times u du, and that's not so bad. Summing for sine, no good. Summing for cosine, yeah, that worked. That's okay. I need the back sub part, but at least it's not square roots, right? That's all right. I can work with that. Let's think about what would happen in the, I'm not going to write it all out, but let's think about it in the cubed case. If I sub for sine, I'll use one of the cosines, and I'm left with 2. That's not so bad. If I sub for cosine, I'd use one of the signs to get my du, and I'm left with sine squared. Not so bad, right? So this one's okay. Let's think about the last, right? We decided as our fifth decision, we decided that this one is bad, right? That was our fifth decision. If I sub u equals sine, I'll use one of the cosines to get my du, and I'm left with cosine squared. Okay, I can work with that. If I sub that u equals cosine, I'd use one of my sines. I'd be left with 3 of them. I don't like that though, right? So we do have here that I really should sub for sine in this case. I really should sub for cosine in this case. And here it doesn't matter either way. So now that we've gone through all of this, right, what's the pattern here? What is it that we're actually claiming as a rule, as a technique? And here's where we go back to the name. The name is OIGOIG. OIGOIG. So let's look at our pattern here. 1 and 1, I can sub either way. 2 and 1, I want to sub for the one with the 2, right? The one with a power 1 was okay. Power 1 was okay. Power of 2 and 2, no good. Power of 3 and 1. Either way, that's okay. Power of 3 and 2, I sub for the square. I leave the cube alone. I use the cube in my du. Cube and cube, either way was okay. Quartic and a first power, I sub in the quartic. And I use my cosine to the 1 for my du. 4 and 2 was terrible no matter what we tried. This would be awful, by the way. This one's a huge pain in the neck. You got to use power reducing, but even worse. It's just a pain. I readily admit. And finally, when we add a power of 4 and a power of 3, I substitute it in for the sign because the power of 3 worked out nicely, right? When I take 1 out, I'm left with squared. Let's do one last case while it's kind of bouncing around in your head what OIGOIG could possibly stand for. While that's bouncing around in your head, let's do one final case together that I didn't put on the page. But let's up the stakes one more time. Let's do, I'm out of colors that I haven't used. All right, that's fine. Let's do sine to the 4th x cosine to the 5th x. So let's think it through first, right? If I sub u equals sine, then my du would use one of the cosines. I'd be left with cosine to the 4, right? And that doesn't feel particularly great. So let's think about the other way and figure out what's going on. If u is cosine, then my du would use one of my sines. I'd be left with 3 of the sines. Ooh. All right, so wait, so either way, this is, So the question is, what would we rather be left with? 4 copies of cosine or 3 copies of sine? Well, we know what happens with 3 copies of sine, right? We get that u squared is cosine squared, so sine squared of x is 1 minus u squared. So for sine cubed of x, I'd get a 1 minus u squared, but then I'd also get a square root of 1 minus u squared, and that does not seem great to me. On the other side, if u equals sine, then u squared is sine squared. So cosine squared is 1 minus u squared. And that's actually not so bad, right? I just need 2 copies of that. So yeah, it gets kind of big, but at least it's still a polynomial, right? This is a polynomial. This is terrible. And that's the difference. So when we add a power of 4 and a power of 5, we still want to sub where the 4 is, and the 5 is actually okay. I use one of them, and I'm left with 4 of them, which is cosine squared squared. What's OIGOIG stand for? Odd is good. Odd is great. Odd is good. Odd is great. And let's look back at what we learned here, right? When both of the powers were even, I had to use power reducing. And here too, we'd have to use power reducing. This would be a pain. When both of the powers were odd, I could sub either way, right? Odd is good. Odd is great. And when I mixed it, when one was odd and the other was even, one of the subs was better than the other. But at least one of them worked, right? Having an odd number of sines was great because I could use one for my du and I was left with sine squared. Having an odd number of cosines was great. I could use one of the cosines to help with my du and I'm left with cosine squared. Having an odd number of cosines was great. I can use one for my du and I'm left with cosine squared squared. Which isn't so bad, right? Cosine squared, squared. I can work with that. Odd is good. Odd is great. Odd is good. Odd is great. When working with integrals of this type, when working with sine to the n times cosine to the m, we really want at least one of those powers to be odd. Because then when you pull out one of them, you're left with an even number for use with your back sub. So let's write down that general form, and then we'll move on to EFUSOT. Let's write down that general form, and then we'll move on. So what is the general situation that we just realized? We have the idea that if I'm integrating, how do I want to write this? Let's write it this way. If I'm integrating sine to the n of x, cosine to the 2k plus 1 of x dx. And I want you to think about why I'm using 2k plus 1 there, right? Pause and think about that for a sec. Why 2k plus 1? Why not m, like what I just said a minute ago, right? Well, if u equals sine of x, then du would be cosine of x dx. So my integral would become u to the n, and I've got a cosine to the 2k, but then my other cosine is going to become my du. So now what's going on with this cosine to the 2k? Well, that's a u to the n, and I can write this as cosine squared x to the k. And why do we like this? Because it's easy to turn cosine squared into u's. It's annoying to turn a single cosine, but cosine squared is fine, and then I'm just raising it to the k. So this cosine squared will end up being a 1 minus u squared, and that still gets raised to the k, which might be a lot of terms, right? The bigger k is, the bigger this gets, but it's still doable, right? It's still a polynomial. And that we can integrate without too much trouble. So not so bad, not so bad. On the other hand, I'm not going to write it all the way out this time, okay? On the other hand, though, if this was just 2k, if it was even instead of odd, then when I pull out one of them to use for my du, I'm left with an odd number, which means I can't easily write it as cosine squared to a whole number power, right? We'd get a square root somehow, and that would be annoying. Odd is good. Odd is good. Odd is great. When I'm substituting with sines and cosines multiplied together, I really hope at least one of them is odd. So there's OIGOIG. There's OIGOIG. If we're going to do sines and cosines, though, we should probably also work with some trig. Some other trig, I should say, right? Like, seems plausible. So odd is good. Odd is great. No big deal. Let's use, I don't know, let's use some tangents. So like maybe tangent cubed of x and secant of x, let's say, right? That seems good to me. Odd is good, right? Odd is great. So I've made a problem that should work nicely. Odd is good. Odd is great. Both of these have odd powers. This should work out beautifully, right? So let's try it. If u is tangent of x, seems reasonable. I'll get a u cubed. That's great. du is, and you need to know this. This is something you need to know. And if you've forgotten, I will remind you real quick. You should do it for yourself. Tangent is sine over cosine. So perform the appropriate quotient rule. Or if you'd rather use a product rule with a chain rule, right? Cosine to the -1 you could do with a chain rule. And figure out the derivative of tangent yourself again, right? If you've forgotten, that's okay, but figure it out yourself real quick, right? Aside. That's what you should be thinking if you've forgotten. And I'm going to probably put a question here of what is it. So what you get is secant squared. What you get is secant squared. The derivative of tangent is secant squared. All right, so we're in good shape, right? Odd is good, odd is great. I had odd powers. This is going to be great. So of my tangent cubed, I get 3 u's. That's fine. And then I'm going to use my secant x dx, but wait, hold on, wait. I need secant squared. I don't have that. I could force it, right? I could add a square here, but if I do, I've got to do a 1 over secant x also. And I don't think that's going to work out too well, right? Now I've got a u cubed, but I have a 1 over secant x du. And sure, I could write that as cosine x, but we're still left with the problem of how do we write cosine x in terms of u? That does not seem like a good plan, right? I don't like this at all. In fact, it's a little easier if you keep with secant, but it's still awful, right? From sine squared x plus cosine squared x is 1. If I divide everything through by cosine, I get tangent squared x plus 1 is secant squared x. So if I had a secant squared, then I could replace it, right? I've got that u squared plus 1 is secant squared. So if only it was a secant squared, I'd be in good shape. But it's not. It's a secant. I'd need a square root. Okay, all right, never mind. We're okay. Odd is good, odd is great. We're still doing fine. Odd is good, odd is great. Let's try it the other way, right? Let's try it the other way. This should work. This should work. So let's see what happens here. Odd is good, odd is great. All right. Let's try to sub the secant instead. U equals secant x. So du is, again, I understand if you're rusty, that's okay, but you should compute this yourself. You can use cosine of x to the -1 and use a chain rule. You could think of it as 1 over cosine of x and use a quotient rule, however you prefer, but do it yourself. You get secant x tangent x. All right, so let's think about it this time. I'm starting with a tangent cubed x secant x dx. And when I break things up, I need a copy of secant x tangent x dx, right? So that this becomes my du. So what's left if that's all staying together for du? Well, I have tangent squared of x, and that's it. Okay. Well, what did we just say? We just said that tangent squared plus 1 is secant, which means that tangent squared is secant squared minus 1, right? Trig identity. So I can replace this with secant squared x minus 1. That works out nicely. And secant is my u. So, okay, not so bad. U squared minus 1 du. That worked out okay. Good, okay, because odd is good, odd is great. Right? Odd is good, odd is great. And indeed, this worked out nicely. This was okay. But it was only okay in one of the two options, right? When I sub for secant, it was okay. Because I wanted the secant still, that's fine. And then I wanted one of the tangents, so I was left with 2 of them. And being left with 2 of them is pretty good, right? That's fine. When I sub for tangent, though, I wanted 2 secants. Huh. Okay. Let's try one more. Let's try what if we do, say, the integral of tangent cubed of x, secant cubed of x, right? The problem was that I needed more secants than I had, so maybe it'll work this time. If u is tangent of x, then du is, we just did it, it's secant squared x dx, we're okay. So my tangents become u's, that's fine. Of my secant cubed, I'm going to break one of them apart, and I'm going to put the other 2 with the dx so that I have my du. Oh man, we're stuck again, right? This was bad again. I thought odd was supposed to be good. I thought odd was supposed to be great, but we'll have a square root again, right? No good. All right, what about the other way? If we sub u equals secant of x, though, we get that du is a secant x tangent of x. So I'm a little worried. Because my tangent cubed becomes a tangent squared secant squared to get my secant tangent. And I'm not, like, this doesn't feel good, right? Because we've been saying odd is good, odd is great, and now I get these evens. But, okay, hold on, though, because the secant squared is just u squared. I don't really care how many secants I'm left with. They just become u's. That's fine. And the tangent squared would become u squared plus 1 based on what we just did, but that's also fine, right? And for the record, if it were a tangent of the 4, I'd just get this whole thing squared, right? I'd get tangent squared squared. So I get a u squared plus 1 times u squared du, and once again, this is an integral that's not difficult for you to do, right? U to the 4 plus u squared, and you straight up integrate. It's not so bad. So cubed and cubed worked well in one direction, but it did not work with the tangent sub, right? With the u sub of tangent. It didn't work. Well, actually, it doesn't beg the question in the actual meaning of the phrase begs the question, right? That's a very specific rhetorical premise, phraseology, right? Idiom. And this doesn't actually beg the question in the literal logic sense. But it begs the question in the colloquial sense, right? It leads us to wonder, what happens if I do, say, tangent squared of x secant to the 4th of x, right? What's going to happen? Well, if u is tangent of x, du is secant squared of x dx, and I want 2 of these secants, right? I'm left with a tangent squared and a secant squared, and I want 2 of the secants in with my dx. So I get a du. My tangent becomes u squared, and that's fine, my tangent squared, and my secant squared becomes, and here's where I always mess up and I gotta like stop and think about it. It's a 1 plus tangent squared, right? That's what we get. That's what we get. Du, which becomes u squared 1 plus u squared du, right? That was okay. So we have even powers, but it worked nicely because I wanted 2 secants to get used. And after I use 2 secants, I still want an even number remaining, right? An even number remaining. We've been trying everything both ways. We should probably do that here too. If u equals secant of x, du would be secant x tangent x. So let's see here. Of my 2 tangents, I'm going to put one of them over with the dx. Of my 4 secants, I'm going to put one of them over with the dx. So I have a du. My secant just becomes u cubed. That's fine, but tangent's no good. Tangent's no good. Huh. So what do we figure out here, right? Let's summarize. Let's put this all on one page and summarize. There we go. So the first new one we did, the first one with new trig functions, with tangent and secant, is that we talked about the integral of tangent cubed x secant x dx, and we found that the u sub of tangent was bad and the u sub of secant was good. All right, that was our first one. Our next example was that we looked at the integral of tangent cubed x secant cubed x, and we tried a u sub of tangent, and that was bad, and we tried a u sub of secant, and that was good. And we tried that both ways. And finally, we tried the integral of tangent squared of x secant to the 4th x dx. We found that the sub of tangent was good, and the sub of secant was bad. Huh. Odd is good. Let's see if I can get both of these on the same page. Odd is good. Odd is great. is good, odd is great. Except tangent, right? Odd in the opposite piece. When you're trying to subtangent, odd secant was bad. Even secant was good. Except, odd is good, odd is great, except tangent. Except for u subs of tangent. Odd is good, odd is great, except for u subs of tangent. One more time. Odd is good, odd is great, except for u subs of tangent. And notice it's the other piece that needs to be odd or not, right? When we sub secant, odd tangent was good. When we sub secant, odd tangent was good. When we sub secant, odd tangent would have been good. When we subbed cosine, odd sine was good. Odd, nope, wasn't good. Nope, odd sine, that was good, right? The opposite piece, whatever you're subbing, the other one is what needs to be odd to be great. Except for u subs of tangent, where you want the other piece to be even. And it's all based on that idea of how many do you need to steal to easily use your du. You want to be left with an even power so that you can use a trig identity, right? A Pythagorean identity. So we want to be left with an even power. So based on how many you need to steal for the du, you want to be left with an even power. When you sub sine, you steal one cosine. When you sub cosine, you steal one sine. When you sub secant, you steal one of your secants and one tangent. But when you sub tangent, you steal two secants for use with your dx. And you want to be left with an even number still. Odd is good, odd is great, except for u subs of tangent. And of course, I didn't mention cosecant and cotangent here, but that follows a similar pattern, right? The derivative of cotangent is negative cosecant squared. And the derivative of cosecant is negative a single cosecant, a single cotangent. So cotangent likewise follows this EFUSOT rule, right? OIG, EFUSOT, odd is good, odd is great, except for u subs of tangent. And what happens when you're stuck? What happens when you have both evens for sine and cosine? Power reducing. And it's just a big mess. It's just a mess. It's doable, but it's a mess. Odd is good, odd is great, except for u subs of tangent. I'm just saying it a lot to kind of drill it into your heads a little bit. But that is our lesson today. That's what we got. There is a cool thing in your book, Wallace's formula, which we usually cover when we have time, and we skip it sometimes even in the regular, brick and mortar version of the class. So let's make that optional. We're not gonna require that of you. We might if we end up with time. We'll come back, we'll talk about it. But for now, let's make it optional. What do you have so far? You have u subs, including back sub maybe. You have integration by parts, including swingy. That's the trickier version of integration by parts. And now you have OIGOIG with the trickier part EFUSOT, right? So everything has the basic approach and then the trickier bit. U sub by itself and then having to do a back sub, which remember, I can give you an example, right? I call this step here back sub. We u subbed, we got du, but I had to go back to the original u equals cosine to do an additional bit of substitution, right? That's back sub. So u sub is made harder with back sub. By parts is made harder with swingy. OIGOIG, the tricky bit is EFUSOT, right? There is an exception. And thus concludes the lesson. So I'll run through the slides like I always do at the end of my lessons, and have a good day. We did a whole bunch of setup here. We tried lots of integrals, and we talked through what would happen with some, and we did others out. We found patterns. We started with sine cosine, and for both possible substitutions, everything was fine. We talked about sine squared cosine, and one of them was nice, and the other problematic. Sine squared cosine squared was bad both ways, whereas sine cubed cosine was great one way and not so bad the other, right? It was a polynomial. Not so bad. We can integrate polynomials. I just really wanted to avoid square roots. We learned how to deal with sine squared cosine squared by using a trig identity and then a power reducing formula. It's doable, it's just annoying. We went up to a fourth power. And once again, one way was good, the other way wasn't. Because odd is good, odd is great. So if I want to sub for sine, I have an odd number of cosines. Beautiful, no problem. But if I try to find sub for cosine, an even number of sines is going to mess everything up. Cubed and squared, same sort of idea. One way was messy, the other way was nice, because one gives you an opposite partner with an odd power. Sorry, subbing cosine gives you an opposite partner with an odd power. That's great. Subbing sine gives you an opposite partner with an even power. No good. And we did sine to the 4, cosine to the 5, right? Still not awful. Because odd is good, odd is great. We talked about a general case. This isn't all 4 general cases, right? We'd have to talk about this being even or odd and this being even or odd and all those combinations. But I did one of the general cases. And we saw exactly why it works out nicely, right? We get a cosine squared here, raised to a whole number. So we applied odd is good, odd is great to tangent and secant. But we found, unfortunately, that odd wasn't great when I did a u sub with tangent. Odd was still great with a u sub of secant. When I sub for secant, I wanted an odd number of tangents. That worked well. When I sub for secant, I wanted an odd number of tangents. That worked well. But when I sub for tangent, an odd number of secants did not work. With an even number of secants, my tangent sub worked. But with an even number of tangents, my secant sub did not, right? Odd is good, odd is great, except for u subs of tangent. And that was our final conclusion. Odd is good, odd is great, except for u subs of tangent. Have a good day.